So for problem 81 here, it says let f be a function that is twice differentiable on the interval from -2 to 2 and satisfies the conditions in the table above. If now this is key right here, if f of x is the same as f of negative x. And so just a comment here, this basically means that f is an even function. And if that doesn't mean anything to you, that's kind of okay. Basically what that means is that the graph of f is symmetric with respect to the y-axis. So basically in the table, they give you information about the interval from 0 to 2. And then we can use this fact to get information about -2 to 0. So, okay. And it says, what are the x-coordinates of the points of inflection of the graph? So I'm going to show you the long version, and then when we're done, I'll kind of do the whole, like, oh, in hindsight, this could have been a lot easier version. But for this problem, basically, from 0 to 1, let me draw an ugly little picture here. Okay, so from 0 to 1, we know 3 things. We know that if f is positive, we know that the graph is above the x-axis. If f prime is negative, we know that the graph is decreasing. And if f double prime is negative, we know that the graph is concave down. So if I needed to, I could kind of sketch it. So it's above the x-axis, it's decreasing, and it's concave down. So like maybe it would look like that. Oh, that should be a 1, sorry. You know, maybe it would look like that. Above the x-axis, decreasing, concave down on 0 to 1. And then since we know that the graph is symmetric with respect to y-axis, we would just be able to like reflect it over the y-axis and get the graph that's over here as well. So let's erase this so I can see the second column. And then on the interval from 1 to 2, if f is negative, that means it's below the y-axis, x-axis, x-axis. If f prime is negative, that means it's decreasing. And if f double prime is positive, then that means it's concave up. So from 1 to 2, below the x-axis, decreasing, concave up. So this is a sketch that would fit everything described in the table. And then since you know that your graph is symmetric with respect to the y-axis, you could figure out what the graph looks like on the left side of the y-axis as well. So then you could look at your own picture and you could figure out where would the points of inflection be. Well, points of inflection are where your graph would change concavity. And so you can see concave up, concave down. So you'd have a point of inflection at x equals -1. And then it stays concave down. And then at x equals 1, it changes from concave down to concave up. So you would have 2 points of inflection, and they'd be at -1 and +1. Okay, and then in hindsight, after doing all of that, I realized that I completely overkilled that problem. Because in hindsight, if you're looking for a point of inflection, you're looking for where concavity changes sign. And so that could have been done way simpler without having to draw it. You can see that concavity is always a second derivative thing, and you can see that it changes sign at 1 based on the table. And then if it's even, you'd know about the symmetry. So if it changes sign at 1, it changes sign at -1, if that makes sense. So that could have been a lot faster. But either way, I think you're still within a 2-minute, 3-minute timeline for that problem. So there you go.